Thursday, we defined this new term called refraction. Does anybody remember what it was? Does anybody remember what refraction was? What? It's only been like 4 days. What is it called? Yeah, it's the bending of a wave. And of course, for us specifically, it's the bending of an electromagnetic wave. But of course, it does it with any waves. Water waves, sound waves, any wave will bend. When does it bend? When does the direction of this wave change? When does it bend? Good, when it goes into a new medium, when it changes from one medium to the other, something different than what it was coming from. And it does that because it changes speed. When one wave goes into a new medium, it either speeds up or slows down. And as a result of that speeding up or slowing down, it's going to change direction. We gave you a quick analogy on Friday. We'll go through that real quickly again today just to refresh your memory on how this whole idea of refraction, because of a change in speed, works. We have pavement right here, this pavement parking lot, or this asphalt parking lot. We have this swamp over here. We've got these soldiers marching. This is one soldier, here's another soldier, and another, and so on and so on and so on. They're all in a line right here. Okay? If we've got somebody up in a tall building or up in a helicopter looking at them from above, then it looks like a wave front. Basically, it looks like a crest of a wave. If a few seconds later these soldiers are all marching in stride, these guys are all up here. But Soldier 1 and Soldier 2, they've slowed down a little bit because they're now in the swamp. They can't go as fast in the swamp as they were walking in the parking lot. So Soldier 2 is going to be probably about right here. Soldier 1 is going to be about right here. If we join those lines together, or those points together, it's going to look something like this. If we look at a few seconds later, okay, these guys are all going to be going at the same speed as they were before. This guy is going to be in the swamp now, so he's going to slow down a little bit. This guy is going to really be in the swamp, so he's going to slow down quite dramatically. These two guys are still in the swamp, so they're still going to be going slow. And it's going to end up looking something like this. If we look at a few seconds later, once again, these soldiers have traveled further. These two guys are still traveling the same speed. This guy's now in the swamp. This guy's definitely in the swamp. These guys are still in the swamp. So they're all going at that slower speed. We join them together, it's going to look like this. The direction of motion of this wave was this way. The direction of motion of this wave is now this way. Why? Well, because when these soldiers, or these waves, went from one medium to the other, when they slowed down, they changed direction. Refraction is the bending of a wave due to the change in speed of the wave as it goes from one medium to the other. Does that make sense? So we've established that a couple of things change here. Okay, when we're going from one medium to the other, the speed changes. What else changes? The direction changes. In other words, theta changes. What we haven't talked about is this third thing that will also change. Take a look at that diagram there and see if you can identify for me what changes in addition to the speed and the direction. The wavelength. Take a look at this wavelength. Okay, it was this distance between crest and crest. Now it's this distance between crest and crest. So as the speed went down, the wavelength went down as well. Three things change: speed, wavelength, and angle. What stays the same? What doesn't change? We talked about this a little bit in Physics 20. Once a wave has been produced, this property of the wave will never change, Daxon. The frequency, right? These things change. The frequency stays the same. Once a wave has been produced, we can never change the frequency. The frequency of the wave is the frequency of the wave. That's where we left off on Thursday. Now what I want to do is define a new term that relates to this whole idea of refraction. That term is what we call the index of refraction. The index of refraction is essentially a measure of how much a wave will bend when it goes from one medium to the other. And of course, for us, it's going to be in the context of light. How much light bends when it goes from one medium to the other. You guys know, you guys have all seen this before, right? You stick a pencil in a glass of water. Okay, the pencil appears to be bent. Well, it appears to be bent not because it really is, but rather because the light that's coming off of that pencil is bending when it goes from the water to the air. How much it bends depends upon the index of refraction of the water. If you were able to stick a pencil in another clear material other than water, say ethanol or something like that, you would find that the pencil would bend a different amount. And the pencil would bend a different amount because the index of refraction, or the amount that these two mediums, water and ethanol, will cause light to bend, is different index of refraction. Now, the technical definition is not how much light will bend when it goes from one medium to the other. That's how we think of it, how much light will bend when it goes from one to the other. The technical definition is the ratio. The symbol, by the way, is a lowercase n. It's called the index of refraction, or sometimes we call it the refractive index. It is defined as the ratio of the speed of light in a vacuum to the speed of light in whatever medium it is that you're talking about in the context of this index of refraction. So if we want to find the index of refraction of air, we say it's the ratio of the speed of light in a vacuum to the speed of light in air. The index of refraction of water is the speed of light in a vacuum, the ratio of the speed of light in a vacuum to the speed of light in water, and so on and so on and so on. So the ratio of the speed of light in a vacuum to the speed of light in whatever medium it is that you're trying to find the index of refraction of. And we can write that as a pretty simple equation, an equation, unfortunately, that does not appear on our data sheet. Looks like this. N is equal to speed of light in a vacuum, 3.00 times 10 to the 8. It's always the same. And it's on our data sheet. We'll say 3 times 10 to the 8 divided by V. Sometimes we see that written in this way because it's a little bit shorter. N is equal to C over V. What does C stand for? Speed of light in a vacuum, right? So it's the same thing. Again, do you need to remember this equation? Kind of. What's more important is you remember the definition of the index of refraction. If you remember that, then the equation kind of comes nicely from that, right? A ratio of 3 times 10 to the 8 divided by the speed of light in whatever medium. What are the units for index of refraction? Sorry? Good. It's a perfect answer. Nothing. It's a ratio. Okay? If we take meters per second divided by meters per second, what do we get? They cancel, right? And we end up with no units. So index of refraction is just a number that measures how much light bends when it goes from one medium to the other. But really what it is a ratio of the speeds. And you can imagine if it changes direction because it changes speed, then the ratio of those speeds will tell you how much it's going to bend. Each different material has a different index of refraction, however, for each different color. So if we shine red light through a particular material and we find that the red light bends a certain amount, or we shine yellow light through that same material, we find that the yellow light bends a slightly different amount because that material has a slightly different index of refraction for each of the different colors. Now, a lot of times, it's not a significant enough effect to really notice a difference, but sometimes it is. If we shine white light, which is really light that consists of all the different colors of the rainbow, red, orange, yellow, green, blue, indigo, and violet, if we shine it at something like a prism, a triangularly shaped prism, then that white light, or the components, I should say, of that white light, will all bend a slightly different amount. Again, they do that because that prism has a different index of refraction for each different color. Red light bends a certain amount, violet light bends a different amount because there's a different index of refraction for each one. What happens as a result of that? Well, the light splits up. Red light bends the least. Violet light bends the most. frequencies that are high will respond to the material more than frequencies that are low. And therefore, there will be a higher index of refraction, ever so slight, but still different, for high frequencies than for low frequencies. Low frequencies bend. High frequencies bend more. Best example of this that I've ever seen in real life, in person, oddly enough, was completely by accident. I was sitting in a friend's house one day after school. It was about 4:30. The sun was coming around towards the west, kind of the southwest, and it was starting to shine in the front window. In the front window, they had a fish tank there. A fish tank in the front window. This is an overhead view of the fish tank. And at one point, the sunlight started going through the corner, that right-angled corner of the fish tank. And when it did that, that white light coming from the sun, it split up. So that the red light bent, but the violet light bent more. And on the wall over here, saw a perfect rainbow. Okay, red, orange, yellow, green, blue, indigo, and violet, all projected onto this wall as the light went through the corner of this fish tank. Happens all the time. There's a certain time of day, and I've only seen it 3 or 4 times since the time we moved into this building, but there's a certain time of day when you get that effect in this building. Okay, you walk through the atrium. Okay, you've got those display cabinets in the corners of the atrium, 60 degrees, right? 60-degree angles there. You guys know which display cabinets I'm talking about? If you're walking through the atrium, you got those big windows right up high, right? At a certain time of day, light comes through those windows and shines through that one that's right by the cafeteria. Okay, and if you hit it at just the right time of day, and you got to do it, you got about a 1 or 2 minute span where you've got to hit it. If you hit it at just the right time, then you can see a rainbow on the floor of the school. If you've got nice bright light, if it's a sunny day and you hit the right time of day and you don't have a million people in the hallway kind of getting in the way. This process of the splitting up of light due to the different index of refraction of the material because of each different color is called dispersion. And we can see that higher frequencies disperse more than lower frequencies. What if I asked you this question? Which wavelengths disperse more? What would be the answer to that? High wavelengths or low wavelengths? No, low wavelengths. High frequencies correspond to low wavelengths. So if high frequencies disperse more, low wavelengths disperse more. You can see up on the board here now a number of different indices of refraction, which obviously you're not going to have to memorize. Notice, though, that it says specifically that they're the absolute refractive indices for sodium yellow light with a wavelength of 589 nanometers. Why do they give me that little piece of data right there? Why do they tell me it's for sodium yellow light with a wavelength of 589 nanometers? The reality is the index of refraction is slightly different for each different color, right? So if you're going to give me an index of refraction, it has to be for a specific color. Now, most times, we can use the index of refraction that's given to us for sodium yellow light for other colors as well, because it's not that much different. Okay, there's only the odd time when the difference becomes significant. And basically, if it's not immediately obvious to you that it's different, that it matters, then it probably doesn't matter. And we can use that index of refraction for whatever color. Notice as well that the index of refraction for a vacuum is 1.00000. In fact, if we went on in decimal places, it would be exactly 1.000000000 forever. Why? Why does it have to be exactly 1? How did we define index of refraction? The ratio of the speed of light in a vacuum compared to the medium. Well, what's the ratio of the speed of light in a vacuum to the speed of light in a vacuum? 1, exactly 1. Now you can see that the index of refraction of air is very, very close to 1. In fact, so close that your data sheet actually says 1.00. That's what we'll use as we do problems because that's what our data sheet says. It's not exactly 1.00000 because light slows down when it goes from a vacuum to air, but not very much. So it's real close to 1.000. You can see that they go up from there. Notice that the index of refraction is always, however, greater than 1. You can't have a speed of light that's smaller than that's bigger, I should say, than the speed of light in a vacuum. Therefore, n always has to be a number that's either 1 or a number that's greater than 1. Because that bottom number on the equation, n is equal to c over v, that bottom number always has to be either the same or smaller than the top number. As we go up here, you can see we go from 1.00 all the way up to diamond, which is 2.42. That's a really high index of refraction. That's why, in part at least, why diamonds are so valuable, because they refract light so much. And you're going to see here in a little while, because they refract light so much, it ends up causing a lot of sparkling. They're nice. They sparkle lots primarily because they have such a high index of refraction. Again, you'll see why that's the case in a little while. You don't need to memorize these. Okay? Anytime you need this data, it'll be given to you. Most times, that's the important one, and that's given to us on our data sheet. Well, what's this? Snell's Law. Not Snell's Law. Snell's Law. Snails travel really, really slow. Light travels really, really fast. So it's Snell's Law, not Snell's Law. Snell's Law is essentially an equation for us that relates everything that changes together. It relates the angle to the speed, to the wavelength. All three of those things change, right? To the index of refraction. I'll draw a little picture here and label some of these things. Actually, let's do it. Let's create a little bit more space here. Bless you. Here's our boundary between the two materials. And here's a normal line that we're going to draw at 90 degrees, right? Normal in physics means 90 degrees. So a normal line is going to be drawn at 90 degrees to the boundary. Here's our ray of light that's striking the boundary. We're going to call this theta I, the angle of incidence. Here's our ray of light as it goes into the new material, the second material. We're going to call this, this is theta, not theta I, but we're going to call it theta 1. This is going to be called theta 2. So the first material, the second material. It's going from the first material to the second material, and because it's bending away from the normal line, we can actually tell that this one's speeding up. Okay, if it was slowing down, it would have bent down this way. That makes sense? If it bends away from the normal line, it's speeding up. If it bends toward the normal line, it's slowing down. It doesn't really matter for purposes of what we're talking about right now. Bottom line is it bends. It bends because it changes speed. This equation, Snell's Law, relates for us the angle 1 to angle 2, speed in medium 1 to the speed in medium 2, to the wavelength of the light in medium 1 to the wavelength of the light in medium 2, to the index of refraction in medium 2 to medium 1. Notice this last little bit here. This whole thing appears in your data sheet, but I want to really draw your attention to that. We get in the habit of writing sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2. What do you think we write by habit sometimes? n1 over n2. It's not right. It's n2 over n1. And it's on your data sheet correctly, but some of us don't look at our data sheets. We just kind of remember it and make a mistake that way. Why would it be the inverse of that, by the way? Why would it be the inverse? Why would, say, v1 over v2 equal n2 over n1? I'm sorry? The slower something goes, the slower light goes in a medium, the bigger the index of refraction. If the slower light goes in a medium, the bigger the index of refraction. Speed and index of refraction are inversely related, right? N is equal to c over v. If n and v are inversely related to each other, then We're going 1 over 2, 1 over 2, 1 over 2. It's going to have to be 2 over 1 for the index of refraction. You ever going to use this entire equation at once? Never. You're going to use two parts of it. Either sine theta 1 over sine theta 2 equals v1 over v2, or two other parts of it, whatever. All right? Just for review, I made a mistake and I guess put it on this page as well. But there's a bunch of index of refractions, that exact same slide that we showed just a minute ago. Again, we don't need to memorize those, but we will have to refer back to them sometimes. Let's take a look at a relatively straightforward example here. 13.3, page 668. Yellow light. Why do you think they're telling me yellow light? Because that's what we have the numbers for, right? That's what we have the index of refraction for, is yellow light. Travels some water into crown glass. The light rays are incident on the crown glass at an angle of 35 degrees. What's the angle of refraction as the light enters the crown glass? Sometimes in these questions, it's useful to draw a picture. Okay, we don't have to always, but sometimes it can be useful. It's going from water, so this is going to be our first medium, water, and then we have crown glass as our second medium. The light is going incident at 35 degrees, and it's going into crown glass. Do you think it's going to speed up or slow down as it goes into crown glass? I don't know. Water to crown glass? Don't know. Let's look at the index of refractions here. Let's look at water, 1.33. Crown glass is 1.52. Is it going to speed up or slow down? It's going to slow down because it's going to a higher index of refraction. If it slows down, it's going to bend this way. It's going to bend toward the normal line. And this angle right here, theta 2, is what we're trying to find. We know that this is 1.33. This was, I think, what do we say, 1.52? What two parts of that equation of Snell's law do you want to use? Sine theta 1 over sine theta 2, v1 over v2, lambda 1 over lambda 2, n2 over n1. Good. Yeah, good. Let's say sine theta 1 over sine theta 2 equals n2, not n1, n2 over n1. Let's say sine 35 degrees over sine theta 2. This is a little bit ugly to solve for here. Equals n2, which is, what is it, 1.33 or 1.52? 1.52 over n1, which is 1.33. Let's simplify this a little bit here, getting some numbers here, okay? Let's pull up the calculator. All right, let's get sine 35. We get 0.5736. 0.5736 over sine theta 2. Now let's go 1.52, I should say, divided by 1.33. We're going to get 1.1429. 1.1429 on the right-hand side. Now, this is kind of where it gets a little bit tricky. Let's take the sine theta 2 up by multiplying and the 1.14 down by dividing. Let's swap places here. 0.5736 over 1.1429 equals sine theta 2. Let's divide those two numbers. 0.5736 divided by 1.1429 gives us 0.5019. How are you going to get theta 2 here now? You have to use inverse sine, right? So let's go inverse sine of 0.5019. And we end up getting an angle of 30 degrees here. Is that reasonable? We do our diagram. We predicted an angle of refraction that was smaller than the angle of incidence because the light was slowing down. Do we get an angle that was smaller? Yeah, if we get an angle that's bigger, what should you do? Go back and see where you made a mistake, because we know that if light slows down, the angle's got to be smaller. Does that make sense? Yep. Yeah, if you need that chart, you'll definitely be given that chart. The reality is, Jackie, I mean, you've written enough tests now where you probably could predict how it would look. You'd basically get a page of information that would say, use the following information to answer the next 3 questions or whatever. And somewhere buried in that page of information would be the index of refraction that you would need. So, it might be in the middle of a big, long paragraph, but they'll always give you the n, unless you need to solve for the n. And, of course, then you'd have to be given the other piece of data. Okay. It's probably, I mean, unfortunately, Jack, it'd be nice if we were just given a table like this. It probably wouldn't look like this. It would probably be, again, buried in a paragraph or a page of information. But in the end, it's still going to be the information you need. You just got to find it. Everybody get that copy down? All right, let's take a look at these ones, okay? I'm going to make a quick copy of that chart and put it onto this page so we don't have to keep flipping back and forth. And then you can start working on it, okay? All right, if we're good with those ones, let's take another look at another example here. It says a ray of yellow light. Once again, we've got our table that is valid here because we're dealing with yellow light with a wavelength of 570 nanometers, travels from air into diamond at an angle of 30 degrees. Determine the following: the speed of light on the diamond and the wavelength of the light as it travels into the diamond. It's going from air to diamond. It's probably a good idea to draw the diagram again here, although it's not critical. We're going from air up here to diamond down here. The ray of light is entering at 30 degrees. The wavelength of light up here in the air is 570 nanometers, which is 570 times 10 to the minus 9 meters. Probably should have highlighted that or circled it or something to remind us that we need to be in meters. Actually, in these questions, you can actually get away without converting. So if you did forget to convert there, you'd get away with it. But let's get back in the habit of using meters always. We want to find the speed of light in the diamond, the speed down here, and the wavelength of light as it goes into the diamond here. Hey, is it going to speed up or slow down as it goes from air to diamond? It's going to slow down. And if you're not sure why, take a look at the indices of refraction. Air is 1. Diamond is 2.42. It's going to slow down quite dramatically. So it's going to bend toward the normal line right here. We're not looking for theta, though. Okay, we're looking for V, and we're looking for lambda. Okay, I don't care which one we find first. Does anybody have a suggestion for finding either one of those, V or lambda? Tristan? So we can say lambda 1 over lambda 2 equals what? Okay, lambda 1 over lambda 2 equals n2 over n1. That will allow us to find, I believe, lambda 2. Okay, Jackie, what were you going to say? Okay. Lambda 1 over lambda 2 equals n2 over n1. There's other options here, by the way. Tristan's answer here is not the only way to do this question. What were you going to say, Daxon? We don't have the angle, though, right? Yeah, you could. So sine theta 1 over sine theta 2 equals n2 over n1. Find theta 2, and then you could go ahead and use the angles to do that. Sure. It'd take you a little bit longer because there'd be an extra calculation there, but it'd be correct. Yes. The only problem is we don't know what the speed is in the second medium and diamond. You could find it, yeah. So you could find it saying V1 over V2 equals N2 over N1. And then we could say V is equal to half times lambda. Sure. Yeah, good. Lots of different options here, right? Okay, this is what Tristan mentioned first, so let's do that. Lambda 1 is 570 times 10 to the minus 9 over lambda 2 equals N2. Diamond was 2.42. And air, they said was 1.00003 or something like that. We're just going to call it 1.00 because that's the way it appears on our data sheet. Let's find lambda 2. Lambda 2 goes up by multiplying, 1 goes up by multiplying, 2.42 goes down by dividing. We end up getting essentially 570 times 10 to the minus 9 divided by 2.42. It's going to give me 2.3, that's right, 2.35 times 10 to the minus 7. Or we're going to round that to 2 digits, actually 2.4 times 10 to the minus 7 meters. Now we want to find the speed. We've already got the wavelength. Let's find the speed now. Let's say V1 over V2 equals, we could go lambda 1 over lambda 2, or we could go N2 over N1. Got a couple of options here now. V1, the speed of light in air, is 3 times 10 to the 8. V2 equals 2.42 over 1.00. So V2 basically becomes, the 1 goes up, the 2.42 goes down, V goes up by multiplying. It basically becomes 3 times 10 to the 8 divided by 2.42. You get 1.2 times 10 to the 8. Look how much light slows down when it goes into diamond. Like, that's pretty dramatic, right? Well, why does it slow down so dramatically? Because it has an index of refraction that's really, really big. It has a big ratio of speed of light in a vacuum compared to the speed of light in diamond. Yep. Yep. Absolutely. That's the other option. N is equal to C over V. Okay, we know the speed of light in air, or in a vacuum, I should say. We know the index of refraction of the diamond. That will allow us to find the speed of light in the diamond. Yeah, so there's lots of options. I think you guys gave me 3 or 4 already before we did that question, and then we did that question, and he's giving me another option here now. Okay, once we find that speed, of course, and then maybe use V is equal to F times lambda, or something different still. And so lots of options here. When you're dealing with an equation that has 4 parts to it, there will often be lots of options. Is that okay? All right, let's take a look at another one. We'll copy over that table again so you don't have to flip back and forth. All right, guys, if we have no issues with those, we'll move on. Yeah, no, that's not the pretty picture I was talking about. We have to define a term, and then I'm going to show you this pretty picture here, Sean. Total internal reflection, or sometimes we abbreviate it as TIR. Total internal reflection is when light goes from one medium to the other, and as opposed to refracting, it reflects. Well, what does it do that? Let me give you a bit of an analogy here. If I throw a rock into the water, like a rock that has a flat side, straight down at water, what's going to happen to that rock? Well, it's going to hit the water, it's going to go into the water, it's going to change speed as it goes into the water, right? But it's going to go into the water. If I throw it at a bit of an angle as measured from the vertical, so almost straight down, but not quite straight down, so it's kind of like this at the water, it's still going to go into the water. It's going to change speed, and as a result of that changing speed, the direction of that rock will also change as it goes into the water, but it's still going to go into the water. If I increase the angle as measured from the normal line at which I throw that rock to a great enough degree, what's going to happen to that rock? It's going to skip. It's going to reflect off. Total internal reflection is a similar phenomenon that takes place, but it's a phenomenon that takes place with light. Light will reflect off of a boundary between two materials, between two mediums, if the angle of incidence is big enough. If you're above a certain minimum angle that we call the critical angle, then light will not refract. It will not go into the new medium. Rather, it will reflect and bounce off and obey the angle of the law of reflection. Does that make sense? So let's write down a quick sentence about this. Total internal reflection is the reflection of light. Really, we're talking about any kind of EMR, but realistically, what kind of EMR are we usually talking about here? Visible light, right? The reflection of light off of the boundary between two media when a certain angle of incidence is exceeded. Let's draw a little picture again here. Here's my boundary between the two media. Here's the normal line here. Here's my angle of incidence right here. Call it theta 1. Okay, let's call this theta 2 right here. Okay, theta 2 is pretty big, but it's still refracting, right? What happens if I increase the angle of incidence even more? Well, the angle of refraction is going to be even greater. So that's a pretty big angle of refraction now. It's approaching 90 degrees. What happens if I increase it even more? Well, the ray actually kind of skips along the boundary between the first material and the second material. If I increase even further still, then what happens to it? It's going to reflect. That's total internal reflection. The reflection of light off of the boundary between two media when a certain angle of incidence is exceeded. That red angle of incidence in the diagram that I've drawn there is exceeded. That certain angle of incidence we call the critical angle. So the critical angle is the minimum angle of incidence required for total internal reflection to occur. Quick question before we move on here. You see the diagram that's up on the board right now that shows total internal reflection happening. Let's just draw a second diagram for a second. This isn't supposed to be a real pretty picture either. In this material, in this scenario number 1 here, we're going from an index of refraction that is low to an index of refraction, an index of refraction that is high to an index of refraction that's low. How do you know that? How do you know that you're going to a lower index of refraction from a higher index of refraction? It's going away from the normal line. It's bending away from the normal line. So the light's speeding up, right? You're going from water to air. You're going from glass to air, or something like that, right? You're going from diamond to air, from a low index of refraction to a high index, from a high to a low index of refraction. Let's see what happens when we go from n is equal to high, n is equal to low to n is equal to high. We know in that case, the ray is going to bend toward the normal line. Let's increase the angle of incidence here. What's going to happen? Well, it's still going to bend toward the normal line. It's going to be a bigger angle of refraction, but it's still going to bend towards the normal line. Are you ever going to get total internal reflection happening here? No. So when does it have to take place? What do you have to have in place in order for total internal reflection to happen? It's got to be from a high index of refraction to a low index of refraction. It can't happen the other way around. Now, skipping, that's where the analogy with skipping the rock kind of falls apart, right? Because when you're skipping the rock, it's going from air to water. Well, it's not going from low to high to low index of refraction. It's going from low to high. But we're also talking about something other than light. That's not really total internal reflection. It's just an analogy, okay, to help us to understand it. Okay, but that's where the analogy kind of falls apart. Annie, was that your question?
Yeah.
All right, look at this. Look at this beautiful picture that we see on the board here now. Yeah, it is. There are no fish in here. I apologize. I was thinking there was. Let's put one in there, okay? Who said that's terrible? Somebody said that's terrible, didn't they? I heard somebody say that's terrible. I seem to remember saying, and I won't mention who this is, I seem to remember talking to your mother on Thursday night, and you know who I'm talking about, saying how nice of a girl you were, and all of a sudden now you're criticizing my artwork. I take all that back. Oh, sorry. Oh, okay. So basically, it was the same thing as saying it was terrible. Yes. Okay. Thank you. Okay. There's my fish. Do you know what that is? Can you tell what that is? Oh, okay. Then stop criticizing me. Okay. It's a red fish. It's sitting right there in the water, and he's smiling because he hasn't been caught. Now you're standing over here at the side of the pond here, okay? So you're looking in this pond, you see this fish in the pond. What are you going to actually observe though? Well, there's rays of light that are reflecting off of this fish. Okay, those rays of light are coming from the sun or coming from whatever lights happen to be above the pond, whatever, and they're reflecting in a million different directions. Let's pick one ray of light here. One ray of light that's reflecting off of this fish reflects up like this. Now, when it goes from the water to the air, it's going to speed up. So let's take a look at the normal line there. When it goes to the boundary between the water and the air and it speeds up, it's going to bend away from the normal line. So it's going to bend this way. It's going to bend right into that guy's eyes. So what's he going to see? A fish. But where is he going to think the fish is? He's going to think the fish is right here. Because his brain thinks that light always travels in a straight line. His brain interprets that ray of light that enters his eyes as having been traveling in a straight line from the time that it was produced or the time that it was reflected off of the fish. So when he sees the fish, he sees the fish shallower than it really is, and he also sees it a little bit further away than it really is. Does that make sense? He doesn't see it where it really is. Now, let's assume for a second now that this guy backs up. Still got our fish there. Now this guy backs up way over here, further away from the pond. There's still millions of rays of light reflecting off of the fish. In fact, there's still that same ray of light that reflected off of the fish before. But that same ray of light is now, it struck his eyes before and he was able to observe it. Now it doesn't, because now it sails right over his head. But good news, there's more. There's lots more rays of light that can reflect and go into his eyes, right? So let's try another one. Let's try another ray of light. This ray of light may reflect into his eyes, right? Or refract into his eyes. But this ray of light, notice, is striking the boundary at a bigger angle. If that angle is above the critical angle, if it's below the critical angle, then look, goes into his eyes, he sees the fish in a different position still, but he still sees the fish. If that angle, though, is above the critical angle right here, what happens? Yeah, it's not going to refract at all, it's going to reflect. So it's going to go down here. What does this guy see now? He sees nothing. You can't see the bottom of the pond. You can't see the fish at the bottom because the rays of light that were coming off of the fish that would be required to refract into his eyes are reflecting off of the surface. We're not saying all rays of light coming off this fish are reflecting, but we're saying the ones that would be required to refract into his eyes are reflecting. And the reason is because he's standing further back, it makes our angle of incidence greater. If it's a big enough angle of incidence to be above the critical angle, then the light's going to reflect as opposed to refract. That make sense? You guys ever notice that? My most valuable golf club is my retriever, my ball retriever. I've used that more times than anything else except maybe my putter. Use that lots too. Put the ball in the water, and you go to put the golf ball retriever in the water, and it's like you're kind of fishing around, and it's like, you know, you see the golf ball, whatever, you fish around, and eventually you get it. But if you stand back, sometimes you can't see the golf ball. Right? Why? Because you've exceeded the critical angle. Does that make sense? All right. Have a good night, everyone. Test tomorrow. Ask questions during scheduled help today or lunchtime.